Hello and welcome. I'm going to go over some examples on moment of a couple. The first example that I have is a 2D simple example to kind of warm up and refresh your memory on moment of a couple. The problem says two couples act on the beam with the geometry shown. Find the magnitude of F so that the resultant couple moment is 1.5 kilonewton meters clockwise. Okay. So first, when we look at this problem, let me remind you what a couple is. A couple, as the name suggests, is two forces that are parallel but opposite direction and they have the same magnitude. So that would be a couple. Moment of a couple, one other thing that I want to add is separated by distance d. Moment of a couple then would be FD, and that d is the distance between the two forces. So when we look at this problem, we see two couples. We see these two. So we have a 2 kilonewton, another 2 kilonewton, that they are separated by a distance d of 0.3 meters. So that's couple 1. And then we see this one as our couple 2, that we see F separated by a distance 0.9 meters and another force F. So it shows the direction going opposite, but they put a negative F on this one, which is redundant, but we'll keep that. So we have two couples. So let's see. Let's call them 1. Let's call them 2. So moment of couple 1, moment couple 1 equals FD. F is 2 kilonewton, doesn't matter which one. The distance 0.3 meters. So then that would be 0.6 kilonewton meters. I am going to take rotation that goes this way as the positive rotation. So when you look at couple 1, the rotation that they're making is going counterclockwise, which is same as the sign that I want to have. So I'm going to put positive. Okay. Moment of couple 2, if they rotate this way, I'm going to take positive. If not, I'm going to take negative. Equals one of the forces, F. We don't include that negative. And at the distance that they're located, which is 0.9 meters. So this one is going to be 0.9 F. If you think about this as a steering wheel of a vehicle, the way it's rotating is going this way, which is against the sign that I agreed on. So I'm going to put a negative next to it. So total moment, okay, equals 1.5 kilonewton meters, and it says it's going clockwise. So again, it's going to be against my sign, so I'm going to put minus, is summation of those two, 0.6 kilonewton meter minus 0.9 F. By rearranging this equation, I am going to get F equals 2.33 kilonewton. So I've got to pay attention to the units. Force has units of kilonewton versus moment has units of distance in it too, because force multiplied by distance equals moment. So that's why kilonewton multiplied by distance, which is meters, gets us units of moment. So that was a 2D problem. Let's look at a 3D one that has x, y, z, and it happens in the Cartesian coordinates. So it has ijk's. A 450 Newton force couple is acting on the pipe assembly as shown. Find the couple moment in Cartesian vector notation. Okay, so for problems like this, we have to use moment of a couple in vector format. If you remember the equation, moment of a couple is r cross f. This is a vector, and it's moment of a couple. One of the forces in vector form and a position vector. So the position vector is from any point on line of action of one of the forces to any point on line of action of this F. Okay, so let's see. For this problem, moment of a couple, let's see, position vector, doesn't matter which one you start. So you can go position vector A, B, anywhere on the line of action, which is from A to B, cross F. In this case, got to be FB, because you start from point A, you go to point B, and you got to use that force that you're arriving to as your vector format. So R, A, B. Someone might say, hey, I want to start from point B and go to point A. That's totally fine. You can start from point B, go to point A, but when you want to cross it, this time you're going to use force A, because that's where you're arriving to. So basically, it's going to look like this. FB, this is going to be your R, and this is going to be your FA. These are supposed to be parallel, by the way. All right, so let's see. Position vector from A to B. My point A has coordinates of 0, 0, 0.3 meters. My point B has coordinates of 0.4, 0, 0.3 meters. So R, A, B is going to be coordinates of B minus A. So 0.4 minus 0, I. 0 minus 0, J. 0.3 minus 0.3, K, with units of meters. In other words, it's going to be 0.4 I meters. Okay, so that's my R, A, B. Let's just start forming our matrix determinant. So in this case, I just have R cross F, so the first row is simply going to be I, J, K. Hey, this side is a vector, so that side needs to be a vector, so it's okay for my I, J, K to show up. Second row is going to be my RAB, which is 0.4. This time I don't need IJK, just the components. And then 0 and 0 and meters. All I have left is my force B, FB, to turn it into a vector format. I have the magnitude of it, but I don't know IJK. But when you look at force FB, you see that it's only on ZY plane. So it kind of looks like this. I'm looking at it, put an eye, draw an eye here. I'm looking at it this way. So all I see is a Z axis, Y axis, and a force that is like this, 450 Newton with a slope triangle of 3, 4, and 5. So my FB is going to be, the X component of it is 0, so it's 0I. The Y component of it is going to be magnitude 450 Newton. I'm looking for Y component. I'm going to go with 4 over 5 J, and that's going towards positive Y, so I'm going to leave it as positive. Z component is going to be 450 newtons, and I look for Z, so I go with 3 over 5 K. It's pointing towards negative Z, so I'm going to put negative right there, and that is my force F, which is going to go in the third row of my matrix. So it's going to be 0, 360 minus 270 newtons. If you do this matrix, you are supposed to get an answer that has IJK in it. So it's getting kind of busy here, so I'm going to write it with a different color. If you do IJK, you are going to get 0I, 108J plus 144K, and the units are Newton meters for this problem. Okay, let's look at another example. Again, this is a 3D format. It says if F equals 80 newtons, determine the magnitude and coordinate direction angle of the couple moment. Okay, so I go back to my blue pen. All right, so moment of a couple, the equation that we have for it is moment of a couple in vector format equals R cross F. We said that R is position vector from any point on line of action of one of them to any point on line of action of this F, whatever we want to put in our matrix. So let me see. This is a point that I have the information about. So I'm going to call that point. I'm going to call that point and call it point A. Call this one point B. Okay, those are the 2 points on line of action of one of the S. So I can now go from point A to point B, and use the vector force that I arrive at, which is going to be this F in the matrix, or I can start from point B, go to point A, and then use that minus F as my force. So I like to go from A to B. So let's see. Position vector A, B. Point A, let's find the x, y, z of point A. And I'm going to convert the units into meters. So x, y, and z for point A. Point A is located at point 2, x, point 3 for y, and 0 at z. My point B is located at point 3, point 8 in y, and 0 in z direction. So position vector A, B is coordinates of B minus A, point 3 minus point 2, I, point 8 minus point 3, J, plus 0, K. The units are in meters. So it's going to be 0.1 I plus 0.5 J meters. Now, I'm starting from point A to go to point B. This is my position vector. The vector force that I arrive at, I should use it as my force that I put in the matrix. So let's see. F has magnitude of 80 newtons and is pointing towards positive z-axis. So I have the magnitude of it. I have the direction of it. So F in vector format is going to be 80 Newton in the direction of K. I think I have everything that I need to go into my matrix. So my matrix is going to be, this is R cross F. I don't have a dot product. One side is a vector, so the other side should have ijk in it, so that's why I write ijk. And that means, sorry, I have ijk in my matrix showing up, and there's going to be ijk in my final answer. Second row is going to be position vector AB, which is 0.1 I, 0.5 J, and then 0 K. Units are in meters. And my force F that I just found, 0, 0, and 80 newtons. So if you do this determinant, what you're going to get is 40I minus 8J, and units are Newton meters, which is expected because I have ijk on one side. I needed a vector, and that's what I got. It's my vector. So when you look at this vector, it tells you that the moment that I found is in x and y plane. Means there's no j component to it. So now let's look at a figure, see if that makes sense. So think about these two forces being applied at the steering wheel. The rotation you get is this way. As a result, your moment is going to be in this plane. Okay, it's not parallel to x, not parallel to y. It is just the moment is this way. Okay, it's not parallel to x because if you look, force B is at 300 millimeters, the other one is at 200, so it's not exactly straight. So the rotation is also skewed a little bit. So let me draw it kind of like this. So I have y, I have z. It's a little bit different than our figure, and this is x. So my moment, the I component of it is 40, which is right here, 40I. The z component of it is minus j, which is right here, minus 8. So my moment is pointing this way. This is the moment that I just found. Okay? The magnitude of this moment, if I want to find the magnitude, is simply 40 squared plus minus 8 squared, square root of that, and it's going to be 40.79 Newton meters. So I have magnitude of a force, or sorry, magnitude of a vector. I have the vector components. The problem asks us to find coordinate direction angle. If you remember from chapter 2, cosine alpha was the I component divided by magnitude 40.79, which you're going to get alpha from here is 11.3. Cosine beta is going to be the j component with the sine. Don't forget the sine of it. They stick together and they come together. So the beta is going to be 101.3. If you don't include that negative, you're going to get a different angle, which is 180 minus this one. So you're going to get about 78 point something, 0.7. And then cosine gamma is the z component, which is 0 over 40.79. So gamma is 90 degrees. And let's see if that makes sense. Alpha is the angle that the vector makes with positive x direction. This is your alpha, which makes sense. That looks about 11 degrees. Your beta is the angle that vector makes with positive y direction, which is this one, which again looks like 101 or more than 90. And your gamma is the angle that this vector makes with positive z direction, which is this one, which is 90 because this doesn't have any z component. So that's the second part of the problem that it was asking us to do. Let's look at another problem, kind of like more of a practical real life problem. A moment of 8 Newton meters about the x-axis is required to loosen the lug nut of an automobile. What is the necessary magnitude of the two couple forces QA and QC? Two couple forces. So that means QA and QC are parallel, opposite direction, same magnitude, separated by a distance. So immediately the information I get from here, these two QA and QC are equal because they are a couple. So what is the necessary magnitude of the two couple? Or in other words, just find one of them. And B, express the resulting couple moment in Cartesian vector form. Okay, so I got to find a couple and express it in Cartesian. All I know is about x-axis. So let's think about it. We had moment about an axis before, which we did using dot product and all that stuff. But before that, I want to look to see what it means. Moment of a couple is a vector, right? And that's going to be r cross f. Again, this r is from any point on line of action of one of the f's to any point on line of action of this f, whatever you put on there. But also, because it's a vector, it's going to have mxi, myj, plus mzk. It's a vector, right? So it has an ijk components. Moment about x-axis, other word for it is component x of the moment. That's just another way of saying it. So the problem tells us this here, the magnitude of it is 8 Newton meters. And it asks us to find QC or QA, which here I wrote it as F. Okay, so let's see. So let's just go back to this. Moment of a couple is going to be from line of action of one of them. Point C and point A are on line of action of QA and QC. So from one of them, doesn't matter. I can go from A to C or go from C to A. Okay, so I chose to go from A to C. So from point A to point C. And then that means if I choose A to C, which force do I have to use? I have to put QC in this matrix. All right, so let's try to fill the matrix. This is a vector. This is R cross F, so I need ijk. So I'm going to write ijk in my matrix. The second row is going to be position vector R, A, C. Let me quickly make the table I like. X, Y, Z. A is located at 25 millimeters, minus 40 Y and 0 Z. Point B is located at point B. Oh, I don't need B, I need C. Sorry. Point C located at 50, 0 and 0. And I didn't change the units. I just kept it as it is. Okay. So let's see. I might have to change it later. So position vector AC means coordinate of C minus A. 50 minus 25 I. 0 minus 40 J plus 0K in mm. So let's put them in here. And I want to show you that, hey, I'm not going to change the units, but that really doesn't matter. Because let's see, 25I plus 40J and 0K. Keep it as mm and see if that matters later. My force QC, I want to turn it into a vector. I don't know the magnitude of it, that's what I'm trying to find, but I'm seeing that it's pointing up, pointing towards positive z's, which is k. All I have to do is just put QC instead of it. So I have, it's like this, it's not a plus k. So I have 0I, 0J, QC, and I'm hoping to get units of Newton out of it, because this the 8 that someone gave me is Newton meter. So if I do the matrix, I'm supposed to get an ijk. Okay, so I get I 40 QC, and this is mmn. Newton meters. Okay, we'll look at the unit. And then I get minus J. Get rid of row and column. All I have left is 25 QC mmn, and plus K, which is going to be 0. Because if I get rid of this row and this column, 25 multiplied by 0 minus 40 multiplied by 0, 0, So I get 40 QCi minus 25 QCj as my moment. The problem told us that this is supposed to be the I component, supposed to be 8 Newton meters. This one is mm. So yeah, it got me here. I have to change the units. So this is going to be, so I have 40 QC mm equals 8 Newton meters. I need to change this to QC 8 Newton meters. Now this is meters. Okay, so I just changed that 40 to meters, 40 mm to 40 meters, so that's 0.05. If I do this one, I am going to get QC. Now the units match because meters and meters cancel, and all left is 200 Newton, which is the same as QA, 200 newtons. Okay, that was part A. Part B says express the resulting couple moment in Cartesian vector forms, which we have it. It's right here. It's Cartesian vector form. All you have to do is equal QC to 200 newtons. So therefore, my moment, I'm going to continue writing it here, is going to be 8I. It better be 8 because that's what the problem tells us, minus 5J Newton meters. And that is for part B of this problem. Thank you so much for watching this.